All right, folks, I hope you're doing well and excited for us to continue on to Module 8, in which we are going to talk about camera and illumination today. So let's go ahead and begin this module here. And we're also going to, just to back up for a moment, talk a little bit about some of the final projects, which you can find here. I'll update the final project repository link momentarily, so you can click on that and begin your final project when you're ready. In fact, let me just go ahead and show you what this looks like, just so you could get an idea of the final project. And again, this is for spring, so I'm just going to show it here, but it'll be summer by the time you click this link. And you'll go ahead and see what it looks like here. We're going to have the project title. You're going to do a YouTube for the project and then put a few screenshots here that'll be easy to share with the class. Here's a quick look at what the rubric is, and then the actual assignment, again, just so you can see it here in the description. I'm going to slowly scroll through this. There will be some example projects, some things, ideas for projects here, which I'm going to go over more in a few moments here. Just some strategy, which again, I'll kind of keep you in the loop week to week on where you should be. You're going to build this sort of like you did your assignments with a build.py and so on. And then you'll have the video deliverable of your project, because your final project really should be a portfolio piece, something that you could show folks if you're interviewing for a software engineering job, specifically for graphics. But in this case, you would have something to show there. And then just some nice video samples here. So for example, of nice productions that folks have done. In fact, since this is where we're going to start the lecture, these are some nice ones to look at here if you want to pause and take a moment to look at some of these. I know the URL is a little bit nasty to type in, but I can share these if you'd like to see them specifically, or I'll just, again, scroll through this, or you can click on the project when you're ready. So anyway, that's what the final project will look like. You have a lot of freedom on the project for what you can build. Most folks continue on with OpenGL. If you wanted to try WebGL or another API, that is allowed. For summer, one, since it's especially fast, the expectation is you're building something that's, the equivalent of what an assignment would be to build, but, in a new topic area or building off an area. You can see some folks built some new shaders for their module loader, for example. Some folks explored terrain. One person built a Rubik's Cube simulator. Another person built explored ray tracing, which might be interesting for folks not able to take the other graphics course I teach. But those are some options here, and sort of to give you a high-level idea, right? So you have a lot of control and creativity over what you build, and then you'll present it with a sort of YouTube-style video. So that's just a little bit on the project. I'll get into some more of the ideas in a moment, but let's go ahead and dive into the slides to guide us here a little bit. And again, today's topic is camera and illumination. So just kind of working through this here. For our pre-class warm-up, I got a fun one for you. For folks who have seen the Lord of the Rings movies or read the books, even better, you might recognize this sort of one ring to rule them all saying here in the famous Gollum character. But what's kind of fun is in graphics, we've actually got this one equation to rule them all, as I say. This is what's known as the rendering equation, which we're going to actually talk a little bit about today. And the idea is that this equation here, it looks a little bit intimidating at first. And mind you, there are a lot of math symbols here. It looks like something out of Mordor almost. But it's actually how we can simulate how light works in computer graphics, which light is, the big part of rendering, right? The whole physics simulation here. So let me kind of break it down. This is that same equation that we saw at the top. But what's really nice is a lot of folks have worked hard to build some nice visualizations of the actual rendering equation here to show you what this actually means. It's actually not as scary as it looks, and you're actually going to implement something very similar to this model today, actually. So, just to give you a little bit of a intuition of what's going on is we're sort of trying to figure out how much light is hitting a surface on the left hand side, that's where we're sort of grabbing things. We've got some component of light here that's usually kind of stable here. We're going to learn this is called like an ambient light. And then anytime you see a integral, especially in the graphics world, right, an integral is an accumulation of something, right? For those folks who have taken Calc 1 or, maybe up through Calc 3, you learn about integrals being the area under a curve, right? So you're sort of accumulating space under a curve. Or if you take, multivariable calculus, you learn how to do things in 3D, right? The volume and so on using an integral. But that's really what it is, just a tool to accumulate something. So we're accumulating light. You could imagine having multiple light sources to figure out based off of how much light's coming, what the material is, right? Is it something metal? Is it a wood, material? Is it, some other surface, like a fabric that might interact different ways? And then this part here is just the angle. So whenever you see this dot product, right, the normal of some surface and the incoming light. And remember, when we have the hats, that means these things are usually unit vectors, right? So they're nicer to work with. So again, that takes away some of the scariness. All the hats here, we know what those are. And then the DWI here, which I have highlighted here, is the direction of these rays, where they're coming from. So really, and this is actually a nice video to check out. So do click this one. It's just a few minutes long, describing the rendering equation and kind of breaking out the different components. All right, so what this is illustrating is a light, you can imagine, from a laser pointer hitting a point, and then it scatters in a bunch of different directions, right? It sort of makes this sort of hemisphere, if you will. And that's sort of figuring out, well, based off of where it's scattering, how much do we light up this surface here? So anyways, we're going to talk a little bit about this, about how light works and how cameras work, and continue our discussion. This is just my sort of, I wish every equation I saw had a nice sort of write-up here, but this is just another figure that might be useful that someone took time to actually draw here and just annotate the symbols, right? This isn't something you have to memorize for this class, but in graphics in general, it's nice if you're aware of this term, the rendering equation, and it's something you can look back on and see how do we simulate light. So pretty cool stuff. All right, so with that said, we're of course recording here, just some course announcements. Assignment 4 has been released, so you can check that out. We're adding textures to our model loader, so we're getting some really cool, realistic models starting to pop up here. Lab 8 should already be pushed to your repository, so check that out. And as I mentioned, the final project repositories are out, so go ahead and take a look at those. And as I mentioned, we're going to take a look at final projects now here, or rather, sometimes I spend lots of time going through this, but I just want to show you where you can kind of look for some final project ideas. So some things to draw your attention to. There's going to be a team spreadsheet here if you want to work in a pair. I would say about 60 to 70% of people work individually on this project. Doesn't matter if you do or don't, you're graded the same and all those sorts of things. Some folks most folks, again, about 70% of folks prefer working individually, but you're welcome to team up. I've seen great projects both ways. And then just some final project ideas, just to kind of click through this quickly. Terrain is very popular. City rendering, this is a particularly cool one, generating a procedural city, so just with an algorithm, right? If you can generate a cube, then you can sort of do the texture procedurally, right? Just by changing some pixels in maybe a uniform way. And then there's some nice shaders and stuff here. You can do some cool things with terrain. LOD stands for level of detail. Level of detail. So I'll just kind of put it here. And sorry, I'm not expanding this because I'm going to go through this one quickly. Then I'll make the slideshow actually fill the screen. Heroes on their ray tracing idea. Again, just some example projects. Some other ways or forms of handling global illumination here, or lighting, what's called radiosity. Constructive solid geometry allows you to remove geometry. So here's a drill bit coming on the left through the shape and kind of drilling away triangles. Progressive meshes, which I'm going to show you a few student projects, this idea that you can take a model here, like our bunny, which we see on the right, and decimate it or remove geometry or put the geometry back. So whether we want to look left to right or right to left on this, it's kind of a cool thing that a lot of folks will use in games, because you can't have so many triangles processing at once on your actual game, because that'll slow it down. But on the left side, as you can see here, you can reduce them dynamically, and that's a way that you can get more objects on the screen, or objects that are further away could have less detail. Okay, so this idea is also sort of captured here, sort of subdividing the triangles, right? You could just be taking the midpoint and sort of creating new triangles. And the advantage here is if you have more triangles, you have more normals, and we're going to find out that normals are actually important for light, right? We got a little bit of a hint with that, with this idea of a normal map, which we're going to actually visit in the next module when we talk a little bit more about lighting and these kind of things. Here's another mesh decimation, just so you can see the high detailed model and then what it looks like at 0.1% of the polygons. Deforming things, right? So some folks will do physics projects, some volume rendering, animation. If you want, these things are called boids, but flocking birds are a nice kind of simulation to run through. More physics ideas, sort of doing a ball and chain here, which is kind of, or this rope here, physics is kind of cool. Different animation systems. This one shows sliding collision, so you can see this thing sort of pointing towards the edge, and you'll see it kind of slides nicely against the other shapes. Particles are probably the most popular project. In fact, I want to just go ahead and show you something. Don't know why that opened up, but open GL tutorial. The probably most popular project here, I'll give that a moment or so to load, is to do a particle simulation. So something like on the right. On the left is one using GPU, so CUDA and OpenScale, which might be an option here. Whoops, I guess that's going to take a few more moments to load. But this is a good one, and just a recommendation for the projects. If you're not sure what to do, you're allowed to find a tutorial and sort of build off of it. So that's why Particle is quite popular here. Let's see if we can get the internet working here. There it goes. So for example, you're allowed to go to this tutorial here and sort of use this tutorial here to get things set up, and then you can build off of it. So here's building a sort of particle fountain you can see moving. And people will do different things like apply physics, or they'll invert the direction, or change different properties to make it like snow, or different things. So that's just some ideas here. I can build a small game, right? Because as soon as you have a textured model, then having a bunch of models on a scene is fine. And that project might be a little bit more about maybe the data structure used to organize it, and the interactivity, and maybe a little bit of collision. Different shaders are fun to do. This is a technique called cell shading, or there's variations of it, cartoon shading or toon shading. If you want this sort of effect, that's pretty cool. And then I also recommend for folks, especially if you want to go into industry, and we're going to talk about this probably at our last lecture when we have a little bit of time, deferred rendering. So another way to sort of organize your scene here. Okay, so that's just one of the slideshows of ideas, and then a great place to get inspiration is from students here. So I'm going to go, let's go here, and basically at the end of the class you'll get a slide here where I'll demonstrate your project. I'm going to go through Spring here. Here, I promise I'd make this bigger, just to show you a few of the examples here. So some particle systems. This person was doing some interesting things with like lasers and collisions, which was cool. Some water, fireworks. This was a nice example of particles, so you can actually see this. And this student here, Cameron, did a nice job. Some students will also apply GIFs, animated GIFs of their project, which is cool. Ray tracing. A lot of folks will use the Peter Shirley ray tracing book, which is what we use in the graphics class, which is useful. Some random simulations. Every once in a while I show up on these projects, so it's funny. This person did the Rubik's Cube simulator, so we've had two of these. some terrains, which we will get into, in Reddit visualizer here. What I learned here, I see Northeastern is here. That's cool. Some more terrain stuff. Let me skip through some of these here. More solar systems, a little game, a shader library. This one had a really nice presentation here. This is a physics simulation here. This one's on Drive, so I can actually show you without getting a copyright notice. Or let me just show it for a second here. But they did some cool stuff here. Let me fast forward it, right? So they built an actual physics sort of simulation here. Let's see, let me speed it up here just a little bit. Yeah, let's see. So again, you can kind of see, just about a 3-minute video is about the right amount of time. I'd say 3 is about the magic number. If you hit 2 minutes, that's fine. If it's 4 minutes, that's probably reasonable. Oh yes, they were simulating tons of stuff here, so about how it slowed down and talked about why. But this was pretty cool here. Yeah, they sped it up there so you could see. I think they had a nice. They were inspired by actually another tech demo they had seen at NVIDIA. So that's something, if you see something cool in a video game you like or a demo, you can be inspired by that, right? So there were some waves. This is from one of your TAs. Some other things here. Here's the deferred rendering. So for those who are interested, you can go in here and essentially just do a search for something you're interested in. And there were lots of terrain projects. In fact, this is a nice one. Way back in 2018 by this student Ben here. I'm just going to show this quickly for a second. They did sort of, let me turn the volume off, but levels of detail, but to render massive terrains here. And you can see there's multiple different textures on it. So they did a really nice job here. They've got fog and some other effects they played around with, which is super fun here. So anyway, I just want to give you an idea of what's possible. A great way to do this to see sort of scope or scale is to look at some previous projects. Let me show. Here is the mesh decimation one. So you can see removing triangles from the actual mesh here, which is pretty cool. I think there's a few decimation ones. This is a research area of mine, so I enjoy it here. So you can see it again here. Let's see. I think there's one by Jackie here, removing triangles. And you sort of do this using a heuristic, right? You can come up with one like remove the longest edge first, or maybe the shortest edge, whichever you might think gives detail. Remove edges depending, or faces depending on where the normals are. So maybe they're away from you. So these are all ideas here. Here was another mesh decimation one. Okay, so that's sort of the scope here. People will do chess. So spend some time to kind of just flip through here. I would say if you have an idea, folks will do games and stuff. This was an actual removing geometry one. And a lot of the folks from another one of your TAs. I'll try to find all the TAs projects here. There's one more from Sam Marine on Sky Lantern, so doing stuff with lighting, which we're going to learn about. TAs have done a wonderful job, so proud to show their projects. But anyway, look through this PowerPoint here. Get some ideas. Even come into this with some ideas of your own, and then you can kind of see scope here. There I show up again. But of what can be done here. Again, here's the ray tracing one, which is nice. Now you won't be able to click on these links, only I can, but you can watch the videos though and get some inspiration. So definitely do that. I think it's a good thing to do. All right, so with that said, that's about what I want to say about the projects, and I'll get us moving on here for this lecture here. Because last time, we really took a big step forward in adding some detail, to our projects here. We're getting some textures here. And once you get that on your model loader, as I mentioned, you're there for building a game, right? We can transform things, we can texture them and add detail, and things are getting interesting. And then we talked a little bit about some other trade-offs we can do with things like mip mapping, for instance, to add detail and just get rid of some noise. And this is something that OpenGL can do again for us automatically. There's GL enable mip map flag, and it'll generate the mip maps for us. Okay, and then then as I mentioned, next lecture we're going to talk about normal maps, but we got a brief introduction into that. So then we're going to really add some detail, but we have to learn about lighting a little bit that we're going to do today. So today is all about lights, camera, and action, getting things to move and kind of creating our scene. And so for our goal today, we're going to have a little scene set up. It'll look something like this. I think I've moved the brick wall a little bit. But the idea is now we have some textures, we're going to have a wall, and then we're going to add a light to it, and then some cameras so we can move around our scene. Okay, so I want to review camera here, the view matrix. So we talked a little bit about it, right? We talked about this thing called the model view projection, or MVP matrix. And really what we've had in our previous lab, so lab 6, where we learned about the projection matrix, or at least applied one, right, when we did the colored triangle with the red, green, and blue vertices, we had a projection matrix that we multiplied in. Our view we didn't really have. We were just viewing it from the origin. So we want to talk a little bit about that. And then our model matrix, right, that's just when we're moving some object around. We're transforming it, right? So we go from its local space into world space. Okay, so let's just kind of take a look at this, just as a brief recap here. The model matrix, is something taking our geometry, again, from our vertices and moving it, right? We're just saying, hey, vertices, I want you to position here in our giant 3D world. Translate, rotate, scale, shear, any of those operations, okay? And we have this model transform matrix in a class called transform HPP now, okay? So we can use that, okay? And it's got different things encapsulated in our abstraction for our model transform, okay? So that's just the how we're transforming our actual object. Okay, so you can see how this is being used in GLM here. I've commented this as heavily as possible in transform.cpp, but each object has a model transform, and then we call the associated GLM translate, which takes our matrix, whatever state it is, and translate it by this vector, or maybe performs a rotation, okay, or maybe a scale or whatever operation we might want to do. Okay, so that's the idea. Okay, so that's how we move this object here, the monkey, which has the name Susan here, from a location. Now, once we moved our objects around, remember this is sort of like being a movie director. Then the movie director comes in with their camera and they sort of place their camera on the set. Okay, and they say, hey, this is, we've moved all of our objects around, right? They're not all just stuck at the origin here, but now how do we want to view the world? Okay, so this is where we get to position our camera, change the angle that it's viewing, and so on. Okay, so that's what we're doing here with our view matrix. Okay, and when we do this, we are now in the view space. We're viewing our scene, okay, as it should be viewed. Now, this is actually, this diagram up here, which I'm sort of walking through here, right? First, we went from translating or moving our object from local space to world space. Okay, and then from world space we went to view space, and again, just paying attention to this transformation, here we are, just in view space. We can see what objects are going to be in the scene. But it's not enough to just see the objects, but then we need to figure out, again, the movie director, what kind of shot do we want? Do we want a wide angle shot? Is it going to zoom in a lot? What's the perspective going to be? Okay, so that's this next step here where we apply the projection matrix, right? This is the P and the MVP step here, where we say, okay, this scene, objects that are farther away should appear smaller. Okay, that's what this matrix is versus the orthogonal matrix, right? So we went from this view space, which is, here's some objects, to you can actually see the objects. Now they have some depth to them and they look like there's perspective. Okay, so that's what this step is, or why we multiply in the projection matrix. Okay, so its job is, and I'll show this in another slide. Essentially, actually, let me just go ahead and show you here. Here's what we're sort of left with in view space. Here's all the things we can see. But then when the projection matrix is applied, you'll notice that, right, it's getting applied to these objects, right? Each of these objects. The vertices are moving, right? We're applying a projection matrix to it, right? GLM perspective, which I'll show you the syntax. And it's sort of smashing things into this unit cube, right? You can imagine this is our film plane here, and this is how we're going to see stuff. Okay, so we see something that looks like this. Okay, here's our objects. We can see objects that are further away, or a little bit smaller. This gives us some perspective, right? In that perspective view, again, everything that's further away kind of converges towards the center, and that's how we get a perspective view. Okay. And then the final sort of transformation at the end here in screen space is just this idea that, well, our coordinate system here, sorry, this is a little bit subtle, is just sort of 1 to -1 here, or however you want to draw this. I guess I could draw it, the origin in the center here might be a little bit more clear. But we have to translate the points to whatever our screen space resolution is. So most of our monitors resolutions are 1280 by 800. All right, let's see if I can, just for example, I'm on my Mac today. If I hit on System Preferences, here, let me move some stuff around, find the right window. Whoops. Not this one either. Sorry. Move this here. Oh, it's not going to let me. Anyway, go to Displays, just to keep everybody in the loop here. And you can see, I can adjust my resolution. I'm not going to do it while it's recording because that messes up things, but I could change the actual resolution here. All right, so that's that there. Whoops, let me get back into here so you can see how I'm recording. All right, so in our code, what does this mean though? For actually applying this MVP matrix here. Well, again, our view matrix, or where our virtual camera is, it's just been fixed at the origin, okay, just in the middle of the screen. So we want to be able to modify this view matrix in some way, okay? But what are the pieces of our actual camera, right? We know we have to at least move the camera, okay, but what about if we rotate it or turn it or these kind of things? So I just want to give you a little bit more intuition about that, and that's what you're going to get to practice for part of your lab today, moving the camera. So what you're going to be given today is a class that looks something like this. It's called camera, conveniently. And the three important parts, or where I want to start us off, is by thinking about these three vectors: eye position, view direction, and the up vector. Okay, and those are highlighted here. They're member variables of this class. And these things get set up in our constructor. Okay, and then we'll modify these if we want to move our camera in some way. Okay, so just starting with the eye position, this is where the camera sits in our world space. Okay, so this is just some vector that says, hey, where am I in X, Y, and Z? Okay, and this is where we want to translate and position the camera. So here you can see this camera has been positioned on our z-axis at 0, 0, 2 here. Okay, so it's where our eye is, if you want to think about our camera as an eye into the world. Where are we positioned? Are we in New York City? Are we in Boston? Are we in Rhode Island? Where are we? Translate it to that location. Okay. And then, we'll have some member functions here, which I've listed as move forward, move backward, move left, right, up, and down. And then you'll figure out, hey, what does it mean to move forward in the world, backward, left, right, etc. Okay. And that can change based on how you're rotated. So it doesn't have to necessarily be, how should I say, X +1, m_eye position dot x +1. Well, again, we have to think about where we are looking, right? Taking a step forward, if you're turned to the left versus, not, is different, okay? So that'll be part of the challenge of the lab here. But I'm going to give you some hints here in a moment. Now, the next part of our camera is where is up in the world. Okay, so usually, and by default, you can just say up in the world is 0, 1, 0. Okay, for this scene and for this lab, this is fine. We just have a flat surface that we're walking on. But again, this is the up vector here for this camera here. Now this one's not quite 0, 1, 0. That's what the y-axis is pointing, but you can have an up vector like that, assuming the camera is just looking straight ahead and you haven't rotated or anything. Okay. Now, why am I talking about the up vector? Well, this becomes useful for one of the functions that you're going to implement here at line 23, in which I'm going to ask you to implement mouse look. Okay, mouse look, for folks who don't know what that is right, if you move your mouse to the left or move your mouse to the right, the camera should turn left or right. Okay, so that's what we mean by the phrase mouse look. But my question to you folks to think about here, and go ahead and pause the video if you need, but given an up vector, how could I implement a mouse look so that I could look left or right with the mouse? All right, and hopefully you've paused and taken a moment to think about this. But let's think about some of our math that we've learned. Okay, so if I want to look left or right, the first question I'm asking me is which. That's a rotation, right? I mean, if I asked you to do this right now, turn your head left or right, your neck is sort of rotating. If it's working properly. Some days you sleep on it weird and it doesn't, but but right, it should be rotating. So that's a rotation. So that means that we need to do some rotation about some vector here. So luckily for us, and the reason that we're using the glm library, and this is your sort of big hint, is you have a function here for rotating a vector here. And then you just have to figure out what axes or what are you rotating about. Again, if you think about if your up vector aligns with the y-axis here, well, you're just rotating about the up vector. Okay, so you can do this experiment now. Sorry, I don't have me on camera, but if you stand up for a moment, take a step forward, and then you sort of turn to the left, again, you're rotating, right? And then your up vector, assuming you're on a apartment or wherever that has a flat floor, you're rotating about the 0, 1, 0 coordinate, right? The y-axis. Now, if you're on a mountain, be careful, but you're probably your up vector is probably either sloping a little bit up or a little bit down, right, depending on the steepness, and that's what you would rotate about. Okay, so that's the idea here and why we rotate about the up vector. The up vector can change, but for this lab, that's what you're going to be doing. You can assume it's just straight up and down. Okay, so that's the idea. Okay, now what if I want to also look up and down in my scene, right? I've sort of covered left and right. Well, we need to rotate about a different vector, okay? And it's not explicitly shown here because you can calculate it, but we have something called the right vector, okay? So you could implement this. You're allowed to add stuff to your camera if you want. That's totally fine, right? This is your code. But the right vector is this thing here. It's highlighted in red here. That's the vector that points to the right of the camera, right? So if you orient yourself in the direction of the camera, it'll be pointed to the right here. And we can compute the right vector by, well, if we have the view direction, which actually is this going to be this blue arrow here coming towards here, and we have the up vector, we can compute the right vector by taking the cross product of up vector and our view direction, right? Those are the only other things that we have here. And that'll give us something that's perpendicular and to the right side. Now we do have to take these in the right order to make sure that we get a vector that's pointing to the right. So you can experiment or try those in different orders if you want, because otherwise you'll get a left vector, and that's a little bit different. But again, if you want to look up or down, then you'll be doing that same rotation, but it'll be about the right vector, right? You'll be sort of turning on this right vector. Okay, for the lab, I just have you do left or right, but it's kind of nice if you can look up or down as well. All right, now let me talk about this other member variable here, the view direction. Again, this is telling us which direction we're looking. Okay, so maybe initially we've been looking sort of down the z-axis. So again, if you do your right-hand rule, right, your pointer finger up straight in the air, your thumb to the right, and then your middle finger towards you. Right, that's the positive direction. So you're usually looking out, along the z direction, probably in negative z for us. Right, so that's emulated here, right? Positive z is towards us, so we're looking down the negative z direction here. That's our initial view. Now this view direction is going to sort of change as we rotate, so keep that in mind, right? If you're using the mouse look, then what are you updating? Well, probably the view direction. Okay. All right, so that's these are our components, and with this we can get a pretty decent camera, right? We can look around. We'll be able to look at least left and right, and then if you give yourself a right vector or just compute this on the fly, then you can look up and down, and then you'll be able to walk with your camera, and that's enough to get us quite far here. Now some notes about the camera class design. It's actually a singleton class, okay? So you might have noticed something kind of wonky here, but in the private section here, that's where the constructor actually is. So this means we're actually not able to construct this if it's private. Again, this is going to be a little bit weird for folks who haven't done a lot of C++, but maybe you've learned this design pattern in OOD or seen it. But the idea is we're only going to have one camera allowed, okay? And that that pattern, design pattern, is called a singleton. Okay, so it'll look like this, and you're given this, right? You don't have to implement it, but it's something to know. What the advantage of the singleton, I suppose there's two. From a design standpoint, we've given this constraint that we're only allowed to have one camera, which for most games and things, that's appropriate. But it also just makes the camera globally accessible. We're only going to have a single instance that we can have. So you'll notice in the camera constructor, it's a little bit weird. This is a little C++ thing, but I've got camera : instance, which returns me one instance to this camera. So it's static. That means it's only created once here within this scope. And then we return that memory here. We dereference it. Because it's a pointer, so we get the actual camera and return a reference to it. This is something as an R value in C++, but you can just think of this as, hey, give me the one camera object that exists. Okay, so you can refer to it anywhere, right? So you're going to notice in your code when you want to use it, you do camera : instance, calling this function, dot move up. Okay, and that'll call move up and move your camera around. Okay, and then when you actually want to use this camera, you're going to have a function called get world to view matrix, and this returns the view matrix for you. All right. Another just aside here that could be useful, just some other useful functions that may be worth implementing. A look at function. A lot of folks will use this if you want to just target a particular position. It's useful for, setting up a scene, or, you could have a whole camera that is just using a look at function. If you like. And there's a nice article here on Scratch Pixel. I'll click on this here. It's just like 2.5 pages or so, talking about how you implement this. Okay. If I had a camera and I just want to look at a particular point, I'm actually going to give you something like this later in the class. We're going to need this when we have to position multiple cameras. So we'll eventually abandon that singleton pattern, but have multiple cameras, and then be able to point to a specific location. So I describe it a little bit here. It's just an aside here if you want to look more at camera stuff. Okay, so the MVP, or model view projection matrix in the support code. Again, just some things that you're going to see just to make you aware of them. Each object that you have, again, you're going to have access to that object's its model space, right? Through each object has a transform. Okay. So let me just look at this line 127 for instance here, and 128, right? All these are the same, but let me just focus on two lines. So you're going to have this thing called an object manager, which I'm going to explain in the next slide, which is another singleton, and you're going to be able to retrieve objects. Okay, so object 0, 1, 2, 3, those correspond to maybe the grass is 0, this brick wall along here is object 1, there's another brick wall here, that's object 2, and this other object here, that's object 3. Okay, so you just refer to the objects as numbers. And then you'll get the transform for that particular object, because again, every object has a transform. And then you can do things with transform like load identity or translate, okay, which would move something back or forward. There'll be ones for dot rotate and so on. Okay, and you'll see the rotations are done in radians as we do. Okay, so that's the idea. And then this was the other thing added to our abstraction, this object manager here, because again, we're starting to get lots of objects. So it's nice if we can just, instead of just creating all these objects everywhere, we've got a class for that. And again, it's a singleton class. That means there's only one of them. But this is a way to add objects, remove all the objects, update the objects, retrieve a specific one, and so on. If you wanted, it might be fun to write a get object, and you could put a name of the object and give them names instead of numbers. But there's different ways to work with things if you want that way. All right. So again, within your objects update function, you're going to see an MVP matrix, so the model view projection matrix built per object. We could probably do this a little bit more efficient. In fact, what some folks will do as well is they'll pre-multiply the model view projection matrix and then only send in one uniform. That's fine. But I just want to show you all the steps, I guess, one at a time here, and you can make it more efficient. But you'll see this pattern here where for each of the shaders, and again, every object has a shader, you'll set the uniform, for that particular object, its view, its projection, and so on, and just pass in the that transforms matrix. Okay. Okay, so I do that for the model, the view, and the projection. Okay, and again, per object, we set up this projection matrix. Could we do this more efficiently? Yes. In fact, this should probably belong to the camera class. Might be a better place for it. But you could change it, or you can change it on a per object basis, which would be kind of neat. So depending on if you need that flexibility or not, it's there. All right, so here is the GLM perspective command. We used it once briefly again in the lab here, but just the different pieces here. You've got your field of view, your aspect ratio, and a near plane, which says what are the closest objects I can see, and the far plane, what are the furthest away objects. If you want to think about these in units, I can see things 0.1 meters up close to me, or I can see things as far as 20 meters far away from me. Okay, you can sort of do this experiment if you want. If you put your index finger close to, just above your nose, all of us actually do have a blind spot where we can't see things. So that's one reason to simulate this. But there is another actually. Why else would you think that we need this sort of near and far plane? I want to sort of let you think about this. And hopefully you've paused the video to think about this, because there is an actual justification for this near and far plane, and it's a little bit of a systems-y topic, I suppose. The one and most common reason is for optimization. So if we set the far plane really far away, that means all objects that are potentially visible, if they're 1 million meters or 1 million units away, or 1 billion or whatever, then we would try to render them, right? But instead, if we make it really short, we can just clip away a bunch of details and not have to do that computation. But the second reason is that actually by having a more precise, so something that's a reasonable range, like 0.1 to 20, again, instead of making this just 1,000 or something random, we actually get more resolution to determine which pixels to show. And the way to think about this is, right, a floating point number, right, which is what we have here, 0.1 f indicating floating point. It can only store so much precision within it. Right? We can't represent every single possible floating point number. That's just, 0.3333333, right? Only just so much precision. Then we'd have to represent 0.3333334, 0.3333335, etc. We can't do that, right, in binary. We've only got 4 bytes to represent a float. But if I make that range a little bit closer, the reality is if I'm trying to distinguish objects, especially if they overlap, I can do a better job, right? Because my Z buffer is saying, hey, which fragment's closer? And if I only have to care about objects within 20 meters, I can have a little bit more precision, okay? So floating point, as is noted here, which is nicely done by another researcher, Keenan Craig, at Carnegie Mellon, you have more resolution near 0, okay? So when objects overlap, this helps with an issue in your Z buffer, when your Z buffer is trying to figure out which fragment's the closest to you, okay? This helps protect against an issue called Z fighting, where 2 objects overlap and then they'll kind of flicker because you can't tell which object appears over the other. Anyway, that's just, this is some really good, you might get this type of question in a graphics interview, maybe more at the intermediate level, but you could wow some folks if you're able to explain why you need a close and answer definitely this reason here, but if you give them the second reason, they're going to say, wow, we're going to hire this person right away. Good job. So anyways, just to give you the goals on what's going to be the first part of the lab is you're going to implement a camera, you're going to implement mouse look on the y-axis, so the ability to look left and right, and you can do it for up and down. Honestly, it's kind of nice. And the camera part here of CPP is those move forward, move left, move right, move up, move down commands. That's what you'll be implementing. Optionally, if you get through these, implementing a jump or thinking about how you would jump, right? If you press spacebar or something and want the camera to jump up in the direction of the view vector and then fall back down, that would be a nice sort of going further exercise. Okay. All right, so if you haven't already, give yourself a short 5-minute break if you need to digest that content. Maybe peek at the lab if you want, and then we're going to continue on to our next section. All right, so hopefully you gave yourself a little break there. Now let's continue on to talking about lights. So how to illuminate our scenes. Coming back to that pre-class warm-up when we were talking about Golem and the one rendering equation to rule them all. I just want to review something that I brought up very briefly. This idea with lights is we actually have this really neat relationship, I guess, with lighting. And somebody named Lambert, last name Lambert, came up with this and just said, color, which is the scene equation, is proportional to the cosine of the angle between the surface normal and the direction of the light source, right? So we've learned that this angle is, the dot product, right? If I take the dot product, assuming these vectors are normalized, we can just take the dot product of L here and N, and whatever that angle is, right, determines how much to light up this surface, right? So if I moved my light source directly above here, the surface, it would give me a dot product of 1. If I moved it all the way, perpendicular, it would be 0, right? It wouldn't be shining down and hitting the surface, so it wouldn't illuminate it. Okay, so that's how we think about how much color hits a surface. Okay. And then, the actual lighting up of our objects, well, just how do objects light up, right? If you've got a blue shirt on, well, that's because blue light's reflecting from that object, okay? So that's sort of our model of light, from a physics standpoint here, right? What color is reflected back and not absorbed into the object, okay? Based off the object's materials and what frequencies are sort of absorbed or reflected back, that's how we get color here. Now, of course, objects in the real world have limitless combinations of colors, right? I don't know what the exact resolution is, but we've been working with RGB in the range of 0.0 to 1.0, or in our PPM 0 to 255, something in that range here. So for us, if we're following this sort of model of what light gets reflected back, right? That's what we're talking about with our RGB intensities. Okay, it's sort of this additive versus subtractive model, I guess. So how do we do this? Well, what we're gonna do if we want to create lights is we're gonna start off on our CPU side by just create a light color like this. And these are gonna be vectors. These vectors will represent R, G, and B values. So if this is 1, 1, 1, this represents a white light. And then maybe we'll have some other color here, 1.0, 0.5, 0.31, something like that. And multiply them together, right? So maybe this is just the color of the object, and if we shine white light on it, this is what color the object will appear. Well, whatever its intensities are in each of these red, green, blue channels here for the toy color, okay? All right, so for us to implement lights here, we're essentially going to do that to create some vectors with different light colors and then eventually position them, okay? Now, in the olden days in OpenGL, it was kind of funny because you just had, GL underscore light underscore 0, and you would just create a light, position it, and you're allowed to do like 8 or 16 of those. But again, cool thing about modern OpenGL, we can have as many lights as we want, okay? But we just have to create them, okay? So if we want to add a light into our scene, well, what are we going to do here? Well, into our shaders, we're just going to have some uniform. And again, I'm passing this in through a uniform because I might want to change this color every frame. In theory, you could just have this in your shader if you knew you always wanted a red light here, 1.000. But we're going to pass it in through a uniform so we can change or maybe create lights on the CPU side. So that's what we'll set up, a uniform for it. And because we're using a uniform, that means our fragment shader, which our fragment shader is what's going to be responsible for lights, because remember, fragment shader is responsible for rasterization and figuring out the final color of every pixel. And we want to be able to color every pixel, based on the light source. Okay, so again, we need our uniform. It's got to match exactly the same capitalization, spelling, etc. that we pass in from our CPU side, and then we have this available on our GPU. And then, if we look at any of our shaders, we've had this one out variable here, that's some vec4 for our color. And what we're going to do is, well, looking back at where we did the textures, right, we had some kind of diffuse color here. That was basically the texture map of the object. Multiply that by the light. And, well, if I multiply something that's just red here, 1.0 in the R channel, 0 in the green and the blue channels, then that's just going to give me all the red components here, right? I've effectively zeroed out the green and the blue here when I say, hey, the light intensities that we want to reflect back are just red. Okay, so that's why we get this sort of scene here. So you can play around with this a little bit in your lab today by just taking the one out variable and multiplying it by something and get something kind of scary looking like this scene here. All right, so here we've just multiplied in a red light, and we don't get any green or blue light reflected back to us. All right, so that's fine to just sort of multiply in a red light, and that's interesting, I suppose. But we really want a sort of more physics-based model here. Okay, so this is something that we're going to do today called the Phong illumination model. Okay, so our sort of introduction to lighting. So we're going to cover this one here in the middle. But we're going to come up with this model here that says, well, how should light interact with a surface? And you can sort of see, depending on the different lighting models, so here's 3 spheres here in the different lighting models, what kind of lighting that you get. Okay, so right, if you take a flashlight and shine it on a ball like this, if you have some, I don't know, basketball or something you can shine a light on, you'll notice it behaves in different ways, right, depending on the texture and so on. So something like this Lambertian style of shading, might be realistic enough, but then you'll also notice usually if you shine a light against something, you'll get some light reflected directly back at you, and that's what this white spot is. And you can notice it's a little bit different based off these different models, but we're going to focus on Phong illumination in this class here. So let's talk about some of these components here. Specifically the Phong model here. And I'm going to show these things in 3 different ways here. But the idea is we're going to sort of track how light works in 3 different components: the ambient light, the diffuse component, and the specular. So the ambient is just the overall lighting in the scene. You can kind of think about it like a dimmer switch, or the sun, if you want to just, in the middle of the day, when the sun is above you, it's pretty bright outside, right? But at night it's very dark. So you can think about that as the ambient light, just how in general bright are things. Okay, so that's the first part. The second component is diffuse lighting. Okay, and that says light is going to, based off of where a light source is, scatter across that surface, and it's going to scatter uniformly across that triangle, and that'll determine the intensity of that triangle. Okay, so that's what diffuse lighting is. Specular, on the other hand, that's the bright highlights on a glossy surface. Okay, so how bright does a glossy surface, like if you took a flashlight against a mirror or a TV or your cell phone or something, how much of that light's going to reflect back to us? Okay, that's the idea of the Phong lighting model here. All right, so here it is in color, so you can see a little bit better. Again, ambient's just the general, how bright is this surface. Diffuse here, you can see, I've got a triangle here, and you can imagine my light source is in front of the computer screen right now, which you're seeing. So this, it's hitting this side here, so it's very bright. But on the side here, no light's reaching. So you can see that light is uniform across this, these 2 triangles here, not very bright here. The specular component, again, if I'm shining a light right in front of my computer here, is going to reflect back more where I'm pointing the light here. Okay, and then when I combine the ambient, diffuse, and specular on together, I get this final output, and that's my actual light for the scene here. This is on the right here when I add these three components together. Okay, so here it is again. I'll give you a moment just to think about or internalize these. Again, ambient is sort of our dimmer switch. Diffuse is how bright it is, and specular is sort of the the bright spot showing how much light is reflected back to us. All right. So just to give a little bit of the more mathematical or to bring back the rendering equation into this, here's the actual summation for lights. Now, again, it looks kind of scary if I just throw all these symbols, so let's break this down. The first part I want to tell you is I'm just going to focus on this part here. These equations are all exactly the same as the top one, but this is just, you'll notice an R here for the red component, the green component, and the blue component, right? We could separate these out separately. So let's just focus on the thing at the top here. And again, just to show what this is, ambient light. So this is actually, how much ambient light do we have for this object, and maybe some constant here. Okay, so this is just some constant value. We could call this ambient strength or ambient level or whatever you want here. And that's added to the overall accumulation here. So the summation sign, right, which is essentially an integral, right, is just saying how many lights do I have of I lights. Let's just assume we have one. Okay, so for one time we're going to accumulate this light. The diffuse component, which again is just that dot product, that was Lambert, right here, the light angle here with the normal of the surface, and maybe some diffuse component here, right, of the surface, right? So if I have a brick wall, it's kind of orangish or reddish color, so that's what I'm multiplying here. And then I have the specular component here. Okay, I'll talk a little bit more about specular here, but basically the idea is, again, how much light is being reflected back here. Okay, so that's R here. Okay, so that's the idea here. So ambient's just added to our final intensity, and then I have these diffuse and specular components that are just the dot product of how much light is coming in towards us. Okay. Now the specular component's also a little bit interesting because it has this exponential value. So it's going to increase the brightness, again, depending on how direct the light is. That sort of makes sense. That could change per surface, right? If you have something metallic or more like a fabric or something that wouldn't reflect as much light, like a cloth. But that's the idea. So you could change those. Okay. So let's look at these again, just a little bit from an implementation point of view. Again, just starting with the ambient light here. So what you're going to be doing for task 2 in this lab is, implementing the Phong illumination model. Okay, so these slides and some of the support code in the lab write-up will be useful for that. Okay, so again, if you want to add or simulate this light, right, I'm just going to create a uniform variable here called ambient intensity. Okay, and so then here's the uniform in the fragment shader, and then I'll pass in, in our object update where we're doing everything, my shader dot, set uniform ambient intensity, and then whatever you want here, 2.0. Okay, so it's gonna be a very bright scene here. We're exceeding 1.0. We're doubling whatever the light is in the scene. Okay, and then we multiply that in here. Okay, so whatever the texture color is times our light color times our ambient intensity. Right, so you're going to get something like this if this is your original scene here. See how bright it gets? You can even crank this up to 4 or 5 and it'll get super bright here. So anyway, that's the ambient component. Again, it's just sort of a dimmer light switch for how bright to make things. Okay, now the diffuse component here, again, we're going to Lambert. We're saying, hey, where is my light in my scene? So the light has some position. And then from that position that we're at, we would compute some vector to this surface, and then that surface is normal, and then figure out what the angle is. Okay, and then figure out what the dot product is. Okay, so this is the idea here. So here's just another sort of rendering here, showing what's going on. I'll start with the bottom picture here. Again, this is saying that the light source is just directly above. It hits the surface, and then the light scatters uniformly. Okay, so that is if these are triangles, they are all brightened up the same amount. Okay, and this picture on the top has a light source. Here's the angle it's hitting. And it doesn't matter that it hits it at a weird angle. The light still scatters across uniformly. Okay, so that's what we mean by diffuse. It's diffusing equally across a surface. Okay, maybe you learned the term diffusion in chemistry when you're talking about, particles in a solution diffusing or whatever. But it just means that they're moving uniformly here. Okay. All right, so how do we implement this? Well, we're actually going to need those normals for our triangles. Now, there's another helper thing in our abstraction called geometry.cpp, which is where we're actually creating our triangles now. You'll notice that I already have the normals implemented for you for most of these shapes, right? Compute these triangles and then the normal, okay? I think I might have cheated too and just said that they're all facing forward. So that you can just make it simple here, okay? So we'll have a new buffer layout for our triangles because of that, because we need to pass in the actual normal information. So we'll pass in positions, normals, texture coordinates, and I'm actually passing in two other things because we'll be using them for your assignment 5, the tangents and the bitangents. We'll get into that a little bit next week. All right, so again, now how do I compute the diffuse lighting? So I've got the normal of my triangles, right? That's what I'm passing in here now. What I'm going to need to do in my vertex shader, because that's where the normals are. Why is that? Well, remember we're creating from our buffer here. That's where we're doing all this stuff with the vertices and the vertex specification, and right, we have our vertex positions, our texture coordinates, normals, right? So these are things going on in our vertex shader that take in the vertex buffer object. That sort of makes sense. Vertex shader, vertex buffer object. That's where those operations are being done. So we need to pass out from our vertex shader each time something called my normal, which was basically just saying, again, I'm passing in the normals, and then I'm going to pass into the next stage my normal. That's how I get information from the vertex shader to the fragment shader here. And so in my fragment shader, I'm taking in my pipeline, my normal here. Okay, so that's the idea. Okay, and then in our fragment shader, for each of the fragments, I'm figuring out a position, right? So if you can imagine a triangle again, the fragments are all at different positions, okay? I have, the model times, whatever the position is. So I get the fragment in world space by doing this, okay? Okay. Now, once I have that position here, additionally, okay, it's cool if I have the position, I should say, of the actual triangle or the fragment within that triangle, and all these frag positions are going to be, again, the same because the light scatters uniformly. But then the idea is that, I need, my light color, and my light has to have a position as well. Okay, so where is my light? Because that's the only way, if my light needs a position, right? So I can compute the vector from the light to some surface, okay? And then have the normal and compute the dot product. Okay, so here's sort of the final step here. Let me slow down here. Again, here's the stuff that I'm importing. Our normal data, and so on, okay? So here's, and you can take a look at this. I mean, this is pretty much the complete thing that we need here for our diffuse light here, and just kind of walking us through the code, right? The diffuse color, well, that's just the texture. Okay, you could rename this texture if you wanted, right? It's grabbing or sampling from our texture map. That's what the texture function does. All right, we take in our vertex coordinates and the 2D sampler here, right? The texture. And then we compute the ambient light, which is what we did previously. That's just some number here times whatever our light color is. Then we compute the normal direction, right? So we've got our normals. I just call my normal, and we get the norm by normalizing it here. In case that data isn't between, negative 1 and 1. Then the light direction, well, how do we figure out what that vector is? Well, we take the light position minus the fragment position. So what is our surface that we're trying to figure out how much to light it up based off of our light position, and that gives us a vector here. Okay, so we're starting to see some of that math come in handy here. Right, subtracting two vectors or two positions gives us another vector, a direction. Then we calculate the diffuse impact here, which again is the dot product of, well, our object's normal, that was computed up here, and the light direction, okay? And then I'm also doing this thing here where I take the max of whatever that dot product is and 0. So why am I doing that? I'll give you a moment to think about that. Well, again, remember, if I get a negative value, that doesn't really mean anything. The lighting intensities are between 0 and 1.0, okay? So that's why I'm just taking the max of, in case if I get a dot product and it's negative, well, that just means 0. Don't light up that surface, okay? So now our diffuse light, or whatever, it's our diffuse impact, so how much to light it up times the light color, okay? And then for our lighting, now I'm just adding up these components, diffuse light plus ambient light, and that gets me the final fragment color, okay? So here's the full sort of fragment shader here. In fact, it's the same as on that slide here for your GLSL code. Okay, so if you do this, then you'll get something like what's on the right side here. Okay, so something that's, the surfaces are pretty much lit up. The light, I believe the way I have it set up is it moves with the camera. Okay, so that's where the actual position is. Okay, now this is a little bit of a boring scene here, so we got to add one more thing to get our final effect here, and that would be the specular lighting. Okay, so in order to compute our specular light, well, let's talk a little bit about the specular highlight. And this is the sort of how much light shines back at you from the light source, okay? So just sort of studying this picture here, again, we have our light source, the normal, that's new here. But then we're trying to figure out how much light hits back at your eye, okay? So the light source could be, far away, it shines down on some surface, and then we reflect that vector, right? Because we're trying to figure out how much light gets back to you, okay? So this time, what's kind of interesting is notice that your eye here, we've got a vector to, well, what's the fragment that we're trying to light up? And then does that light reflect back into your eye? Okay, so that's the angle that we're trying to figure out. If it's the same, if the dot product is overlapping, right, that means lots of light coming to your eye, right? You get 1.0. If it's in the opposite direction, if for some reason this light reflected back in this direction, right, then you'd get 0 light to your eye. Okay, so that's the idea. So the triangles that are pointing most towards you, right, are gonna light up more. Okay, so that's the idea here. Okay. Now, part of our component of our specular lighting is this sort of specular strength, which is a constant value. And that's the sort of exponential value here. So it's some constant value. And what it's really doing is it's measuring the fall off of the light. So a value of 2 means it's falling off much more slowly. A value of 256 means it's falling off or attenuating. We're going to use this term again. It's much more quickly. So a higher value will give you a sort of bright spot, right? And then it'll fall off very quickly, right? You'll notice that the rest of this triangle here, or these two triangles, aren't very lit up here versus this value here. Okay. Okay, so let's actually see how we do the specular lighting, our final component here. Right, again, we've got to work with the view position, our fragment shader, right? Because we need to calculate again where are we viewing our scene from, right? So we have our view matrix, and that's how we'll figure out how much light comes to our eye. Okay, so now when we compute the view direction, well, we have our initial view position, wherever we're viewing from. Again, this can be the camera position. The direction, well, that'll be our, wherever our camera is minus the fragment position. Again, if our position is 0, 0, 0, it should be eye position. And then we reflect that vector, which essentially is just negating it. And that will determine how much light gets to our eye here. Okay, so we've got our normal of our surface, and then where is the light coming from, and then we reflect that vector. Okay, so let me go back to here. So our normal, where's the light coming from, and then we reflect that vector. That's this guy here. Oops, it's this one in the orange here, indicated by R. That's how much is reflected. Okay, so that's the reflection direction. All right, and then once I have that, the reflected vector, then I'm computing the dot product between where am I viewing my scene from, which again is based off our eye position and the fragment. Let's go back here, our view direction, where are we viewing from, and our position. And then some constant value here, 32. That's our exponential value. Okay, so again, same trick here. Max of the dot product. We want some value between 1.0 and 0.0. And then I take the power of that to give the fall off. Okay, higher value here means we'll have a sort of only a bright spot in a smaller area. That's the fall off that we're measuring. And that's the specular component. And then once we have this specular value, well, then our lighting equation is just the diffuse component plus the ambient component plus the specular component. And that gives us our lighting model. So then I can just multiply whatever our light is times the diffuse color. Remember, that's the texture here, diffuse color. And then we get our final fragment color. Okay, so then you should have something that looks a little bit like this. And you'll notice that it's a little bit brighter here towards the center, and then you get a fall off towards the top here. Okay, so you should see something like this in your actual scene, and then also be able to move around a little bit. Okay, so I have a version of the shaders provided for you, the full things that I believe should work here if you were to sort of work through this and the comments. And I have something similar in the lab provided, but this is just sort of your backup if it's not working or you just want to see everything on one slide, which is kind of nice. So if you want or are able to get in the lab or a second monitor and have this up, this can be maybe useful to see the comments. All right, so with that said, that's the main portion of our lab, but I did want to just, for your graphics knowledge, alert you of some other models here. And you can look in the Learn OpenGL lighting section. This is going to be your reading. That's what's linked in today's module. There are other techniques, right? We saw some, Blinn, Lambert, Phong, which we learned about, but there's another one called Gouraud shading that's worth knowing. And this one only uses the vertex normals instead of doing things per pixel, right, per the fragment position. So you notice our Phong lighting here on the right is quite smooth here. On the left side, not so much, right? It's a little bit jagged, right? Because we're not using as many normals here. So you can almost see the geometry in this shape on the left here. So that's why we tend to use Phong. It's a little bit more computationally expensive, but for a game or something where we want something a little bit more smoother and realistic, the right side is a little bit better here, our Phong illumination model. All right, some other lighting notes, and this would be a really cool final project. It would be pretty advanced, but very cool. But it would be to actually pre-calculate lighting. So sometimes, we're doing our lights every frame, right, when we're calculating this. But in some games, and most games still do this today, they'll use a combination of this pre-computed lighting called a light map, where they take some object in a 3D modeler and then they bake in the lighting. So they'll position lights in a tool like Blender and then bake the lights into a texture to give these sort of atmosphere, right, that it's sort of dark. And it's a way to sort of cheat in a way and get a little bit extra lighting in, because it doesn't cost anything once this texture is loaded versus this one. But then you can come and add your dynamic lights. Okay, games in the past used to solely use this technique with no dynamic lights, or maybe a few because you only had a handful. But this is a cool technique where you can imagine adding a few lights in different places and doing this. Okay. So again, we covered sort of ambient lights and what those are. There's different models for the lights themselves: directional lights, point lights, area lights, emissive lights, so things like neon signs, things that actually emit lights, lightning bugs. Area lights, which just have sort of a fixed region but fall off really quickly. We're going to implement point lights next week as we learn a little bit more about lighting. So again, the lights themselves can change. We're implementing today essentially a directional light in a way, and then we're going to implement point lights. Okay, so anyway, just a little bit more knowledge there. Your goals for lighting today is going to be implement the diffuse lighting and specular lighting into the scene, and ambient, I guess, it's just the Phong illumination model. Okay, you'll spend some time, implementing from this sample code here if you want, or the lab, or Learn OpenGL is actually get a good walkthrough. That's what I've tried to follow for today. There's a few more videos on diffuse lighting here if you want to just hear another perspective. I think this can be useful. This is a nice one here. I'm going to click on it. I think it's by Jamie King, who's got a lot of other nice tutorials here. So I'd recommend that one just for more understanding of lighting here. Okay. So here's your lab goals. Summarize what you're doing in the first part for camera. Again, that mouse look and moving the camera around. And then for lighting, implementing that Phong illumination model. And, really after today, we're in an exciting point in this class here with our lighting. Okay. All right, one last little aside just on this term known as instancing. Just to make you aware, what's kind of cool, or what I've done, and it's subtle, but you're going to notice that in our abstraction as you peruse around this geometry class, I only, for our triangles that I make, everything's made from the same two triangles in the vertex buffer. Because once you can make one quad, you can make as many as you want. It's just about rotating and translating them in different ways. And this is called instancing. Okay, so we don't have to send separate necessarily vertex buffers in for every object. Okay, that would be the idea to optimize this actually, to use instancing. Okay, so it's a great optimization. Okay, and you can do these little tricks by only drawing using GL draw elements to make things more efficient. So I just wanted to make that aware if you notice that, hey, we're drawing the same quads over and over again, could we do something more efficiently? All right, so go ahead and stop there. You have your in-class activity as well. Let me go ahead and open up the Mono repo for summer, just to show you where Lab 8 is. And again, it is here. You'll have your camera tasks that you're doing. There are some other notes here about refreshing on the singleton if you didn't quite understand that part. And then the lights here, sort of getting you ready with your shader here. Okay, with some more tips here. Okay, so worth reading some of the code and getting prepared in that way. But I think you're in a good spot. And as always, visit during office hours. Post lots of Piazza questions. Folks have been doing a great job with that, so happy to continue that discussion. All right, folks, hope you're well. I'm going to go ahead and stop our recording here, and we'll talk to you soon.